right, welcome to the Chapter 1, Part 1 notes. This is going to be sections 1.2 and 1.3. So starting with section 1.2, we are defining points, lines, and planes. So this is our basic geometric shapes, and our objective is to understand basic terms and postulates of geometry. So first, we're going to start off by defining a point. Now, you are hopefully familiar with how points are used, but you might not have a formal definition of a point, and so that's what we're aiming to do. And a point is actually very difficult to define because even though we draw a point as a dot, a point technically has no size. It's just a location. Okay, so a point is a location that has no size. And when we're looking at this point here, it looks like just a dot with a label next to it. This one is called K, and so we would describe that as point K. And if we were to write it in a sentence, or if we were describing it, we would say also point, not paint, point K. If we take a point and we put a lot of points next to each other so that they're touching, we get a line. And so a line is the next term that we'll define. And a line is represented by a straight path that extends without end. This has no thickness. So it's points that are just lined up only in one direction. So even though this is represented by a line, I could technically say there's a thickness here. A line should have no thickness. And there's a couple ways that we can state this diagram. We can describe it as line N. That lowercase n describes a line or names a line. So we have line N. Or we can describe it by two of the points that are on the line. So we could say this is also line DE or ED or DF or EF or FD, as long as you have 2 points. So I could also say line FD. Any 2 points on the line can define that line. And how do we write it? Well, we can call it the same way, line N, or we can do DE with a little line and 2 arrows, and that indicates that it's a line. It's important to have both arrows there because, as we'll see throughout the chapter and in these next couple of definitions, there are other shapes where we don't have arrows on both ends of those lines. So if it's a line, if it continues off in both directions, then our notation also needs to continue off in both directions. And we'll use whatever letters we used to define the line are used in naming it as well. Our next shape that we're going to define is a plane. So just like to get from a point to a line, we just put a lot of points next to each other to get a line. If we put lines next to each other, it would extend out into a plane. And so a plane is a flat surface that extends without end and has no thickness. So again, it's kind of like a piece of paper that never ends. So we could draw little arrows, but we would have to draw arrows everywhere. And so we don't usually draw the arrows to indicate a plane. Instead, we will just describe it as plane. This plane is denoted with a lowercase m, plane M, or we can use 3 non-collinear points. So 3 points that are not all on the same line. And we're going to talk about collinear in a second as well. Okay, so in this case, we have points RWT. So this would be plane RWT. And then in order to write this, we will just, again, name it the same way that we said it. So we'll say plane M or plane RWT. So there's not a special symbol for naming a plane like there was for a line. So in defining a plane, we said if we wanted to describe a plane using 3 points on that plane, they have to be non-collinear. So what is collinear? Well, co means together, linear is a line, so they're together on the same line. So collinear points are points that lie on the same line. So if we're looking at this diagram here, which of these points are on the same line? Well, I, J, and K are collinear, which means L is not collinear or non-collinear. So we have I, J, and K are collinear points. Just like collinear means on the same line, if we look at our next definition, it is coplanar, meaning on the same plane. So when we're looking at coplanar points, they're points that lie in the same plane, or you can say on the same plane, that's fine as well. So if we're looking here, J, E, and P are all coplanar. If I were to draw another point here, let's call it K, that is non-coplanar, but it is collinear with E. So J, E, and P are coplanar points. So we have collinear on the same line, coplanar in the same plane. Let's take a look at our next definition of a line segment. So we had a line that extends infinitely out in both directions. A line segment is if I were to cut just a piece of that. Okay, so cutting on both ends, just a piece. Okay, so a line segment is part of a line that consists of 2 points, which are called endpoints, and all of the points between them. So here we have segment AB, or line segment AB. And the way we denote that is with an AB and a line with no arrows, because this time it's not extending out to infinity in both directions. Okay, so if we look up here at IJK, that's a line because it has arrows on both sides, whereas AB is a line segment because it does not have arrows on both sides. So what if it has an arrow on just one side? Then it's called a ray. So a ray is part of the line that consists of one endpoint, so one side that ends, and all the points of the line on one side of that endpoint. So it's one side it ends, one side it keeps going. And we could call this ray BN. We always start with the endpoint, or we can call it ray BY. And how we denote that is we put the BN that we named it with the arrow pointing in the direction that it keeps going. So B was the endpoint and N keeps going. And BY, B is the endpoint, Y, it keeps going past Y. So an arrow on only one side. And what if we have a line and we cut it in half? Then we actually end up with 2 rays pointing in opposite directions. So imagine I have this line and I cut it right down the middle. And then I have a ray pointing JI, and I have another ray pointing JK, and they are pointing in exactly opposite directions because together they make a line. And so that would be called opposite rays. Opposite rays are 2 rays that share the same endpoint and together form a line. So in this example, we have ray JI and we have ray JK. And the way we denote that is JI, arrow pointing in the direction of I, and JK pointing in the direction of K. Okay, so let's see if we can explain why are line segment AB and line segment BA the same. Okay, Well, let's start by using words. Line segment AB and line segment BA have endpoints, A, B, and this one has endpoints B, A, right? Well, what if I turn the page upside down? Well, then couldn't we call this one line segment AB and this one line segment BA? And so we can see that the orientation of the line segment does not affect its name. So we can say these two line segments have the same endpoints and orientation, meaning which way is it facing, does not affect naming the segment. Okay, so if I had a given point A and a given point B, whether I draw the line segment as AB or BA, it's the same line segment. How about if we look at these rays? So we have ray AB and ray BA. Are these different? Well, let's use that same logic of I have a given point A and a given point B. Then ray AB starts at A and goes past B. But ray BA starts at B and goes past A. So are they the same ray? They cannot be the same ray because they have different endpoints. These two rays have different endpoints. Ray AB has endpoint A, right? It ends at A. And ray BA has endpoint B. Okay, and then just to draw it in a way that you can see the two different rays, this would be ray AB, and ray BA is facing a different direction with a different endpoint. So they are not the same ray. Let's take a look at the next page. So we're looking at an example. We need two other names for line QT. So where is line QT? Here's point Q and point T, so the line that goes through it, and we want two different names. Well, notice this line is named M, so we can call it line M. It also has a point N, so we could also call this line TN, for example. Now there are a lot of names that you could use for this line. These are not the only two, but we only need two of them. Part B, give another name for plane P. Plane P is this beige plane, and remember it continues out in all directions even though we can't really draw it like that. Okay, so plane P, we need another name for it. Well, remember for a plane we need 3 points that are not all on the same line. So I can pick R and Q, but then we need a point that's not on that line but is on that plane. So that would be point V. So any 2 points from this line and point V. So we can call it plane RQV. We can't call it RQS because those 3 points are all on the same line. And the reason we don't want to use 3 collinear points is because there are other planes that go through those same 3 points. Okay. Part C, name 3 points that are collinear, 3 points that are on the same line. Now we have a couple options here. We already talked about how this line has 3 points on it. We also said this line has 3 points on it. So either of those will would be fine. So 3 points that are collinear, I'm going to choose to use T, Q, and N. Are collinear. Name 4 points that are coplanar. 4 points that are on the same plane. So we have our plane here. It has 4 points, V, Q, or V, R, Q, and S. So V, R, Q, and S are coplanar. Give 2 other names for line RQ. Notice it has the 2 little arrows, so it's not a line segment, but a line RQ. Okay, well, if we're looking at this line, it could be called line L. And then I need 2 points that are not R and Q, so I could use Q and S. Q and S, and it's a line, so I put the arrows. Now, again, there are multiple names. You don't have to choose those 2, but we only need 2 of them. And then part F, name a point that is not coplanar with R, V, and S. So R, V, and S, what is a point that is not on that plane? Well, we have 2 points here. N and T are both not on that plane. We just need one of them. So let's go point T or point N, either one. Okay. Let's look at the next example. Name segments and rays. What are the names of the segments in the figure at the right? So segments, remember, have endpoints. So which of these have endpoints? Well, I can say D to E, that ends. E to F, that ends. But also D all the way to F, right? So we have 3 segments. We have DE, EF, and DF. No arrows because these are line segments. What are the names of the rays? Okay, a ray means it goes off in one direction. Now I can't say ray D because I need 2 points. I need an endpoint and a point that it goes through. So we can say E through D. So we have E through D with 1 arrow. I can say E through F. I could also say D through E or F. And I can also say F through E or D. Right? So there are actually 4 rays here. We can't start at D, but we could start at E to the left, F to the left. We could start at E to the right or D to the right. Which of the rays from part B are opposite rays? Opposite rays means they have the same endpoint. So here, this has endpoint E, this one has endpoint E. Those are opposite rays. This has endpoint D, is not an opposite ray because this one has endpoint F. So opposite rays have the same endpoint. So E to D and E through F are opposite rays. Okay. A postulate, or also called an axiom, is an accepted statement of fact. So this is a statement that we know will always be true. And we want to make a postulate. So we want to draw 2 points and say how many lines can be drawn through those 2 points. So here's 2 points. How many lines can I draw through those 2 points? Well, a line is defined by 2 points. So I can only draw 1 line through those 2 points. There's no other line that can go through those 2 points. So there's only one unique line through the points. Or we can state that through any 2 points, there is exactly 1 line. Okay. Now, this is kind of a reminder from algebra that when you have 2 or more figures, The points that they have in common, everything that they share, is called their intersection. Intersection is what do they share in common. Let's take a look at the next page. In this example, we want to draw two distinct lines that are intersecting each other. So intersecting means that they cross, that they share something with each other. How many points do these lines intersect at? So I want to draw two lines. Here's my first line. I want to draw a line that will cross this line. And any line that is not parallel will cross this line. You might remember that from algebra. And so here we have a line that crosses. How many points do these lines have in common? Well, the two lines cross only at 1 point. And so if two distinct lines intersect, then they will intersect in exactly 1 point. So this is another postulate that we can use that's a statement of fact that no matter what two lines we have, as long as they're not parallel, so as long as they intersect each other, they will always intersect at exactly 1 point. Not 2 points, not 0 points. As long as they intersect, it will always be 1 point. On this next example, we want to look at intersecting planes. So imagine we have two intersecting planes. Where do they intersect and how many points occur at this intersection? So the way I like to think about a plane is I imagine it as like a piece of paper, okay? So if I have two pieces of paper, and I want them to go through each other, where will they touch? What type of shape is created? Well, we can see here, imagine these are two pieces of paper. Where they touch is all along a line. Kind of like when you open a book, the whole spine of the book is a line, okay? So imagine two intersecting planes. Where do they intersect? They intersect at a line. And how many points occur at the intersection? How many points are there in a line? Well, there are infinitely many points in a line, right? Because a line never ends. And the plane keeps going on, and so does the line. And so if two distinct planes intersect, they intersect in exactly a line. Okay. I know this one is a little bit harder to picture. We can picture lines crossing pretty easily because we can draw it, but planes crossing is much harder to imagine. So try, if you have a book, you can kind of look at what happens when you open the pages of a book. The pages of the book can represent the planes, and where do the pages of the book meet? They meet at the spine, which is a line. Let's take a look at the next one. So part 4, draw 3 non-collinear points, P, Q, and R. How many planes exist that contain these 3 points? So I want 3 points that don't make a line. Well, any 2 points make a line, so it doesn't matter where I put P and Q. But I want the third point not to be on this line. So if I want it to not be on the line, I can put it just somewhere completely away from the other 2 points. So these 3 points are non-collinear. They don't make a line. What would it look like if they were collinear? I would put R here if it was collinear, but we don't want it to be collinear. How many planes go through this? How many pieces of paper can you fit through those 3 points? Well, if we think about the piece of paper that we're drawing on goes through those 3 points, is there any other piece of paper that could go through those 3 points? I could, let's just say I took this piece of paper. I said, okay, it goes through points P and Q. Let's see if I can make it flatter. Actually, here, I have an envelope. Okay, so if it goes through the points P and Q, but it also has to go through the point R, it's going to have to lay flat. And in order for it to go through the point R, it has to be exactly flush against that piece of paper. which means that it's the same plane. So any 3 points, in order to get the 3 points onto the same plane, onto the same piece of paper, they have to be on the same plane. So any 3 non-collinear points go through exactly one plane. If those points were lined up, notice I could have left the envelope standing straight up. If they were all in a line, that's a different plane. I could also have tilted it, that's a different plane. So if they're in the same line, it is not a unique plane. Let's go ahead and do some practice problems. Part 1. Shade the plane that contains point N, P, and Q. N, P, and Q. Okay, I'm going to do this one with you, and then the other 3 I'll let you do, and we'll go through during our synchronous class time. So hopefully you found points N, P, and Q. What plane goes through all of those? What do all 3 of those corners touch? They all touch the bottom of the box. So that is plane NPQ. Okay, go ahead and try these other 3. We'll go over them together. When you finish the try this, we'll look at the next page, which introduces us to section 1.3. And in 1.3, we're measuring segments. So what we want to do is we want to be able to find and compare lengths of segments. Remember, a segment is cut off at both ends, no arrows. Okay? So if we're looking at this ruler and we want to find line segment AD, okay, so ends at A, ends at D, and we want to know what are the coordinates of point A. Well, this doesn't have an X and a Y axis, right? It's just one axis. And so the point, the coordinate, is only going to be one number. A is at -4. What is the coordinate of D? D is at 1. What is the distance between A and D? Well, remember, we can find distance on a ruler by how many segments are there between, or how many cars could be parked in these little parking spaces. Okay, so the distance between A and D could be found by counting, but we can also do it algebraically. And to find the distance algebraically, we subtract the 2 numbers. So we would take -4 minus 1, but distance is always positive. And in order to make a number positive, we take its absolute value. So we would take the absolute value of A minus D. So we're taking the positive distance between the 2 values. And so we can say A is -4, D is 1. -4 minus 1, negative minus, so then we take absolute value. -4 minus 1 is -5. Absolute value of -5 is 5. So we take absolute value of the difference, which is subtraction. Okay, we have a formal definition here. The distance between 2 points, A and B, any 2 points, on the number line is the absolute value of A minus B, where A represents the coordinate of point A and B represents the coordinate of point B. The distance from A to B is the length of the segment. So we want to do the same thing, but now with points B and E. So we're going to take the absolute value of B minus E, find B on the number line. B is at -2, and then E, which is at 3. -2 minus 3 is -5. So again, we have a distance of 5. Now, if we look up at the number line, we could have counted, right? From A to D is 1, 2, 3, 4, 5 units away. From B to E, 1, 2, 3, 4, 5 units away. But if we're working with bigger numbers, then it's going to be more difficult to count. And so we want that algebraic approach as well. Okay, so let's look at our next section here. If we're looking at this segment here, what is the name of the segment? The name of the segment is AB. Notice there are no arrows. What is the measurement of the segment? The segment measurement is 6 inches. Okay, so if I'm talking about the segment, I'm not going to talk about its measurement. I can say segment AB. But if I'm comparing its size, then we're going to talk about the measurement, which is 6 inches. Okay, now when we have segments, and notice on our number line above, it's actually made up of a lot of segments that are put end to end. When we're talking about segments, we can talk about their distances as being addable. So if I have two segments next to each other, I can add the lengths of those two segments to find the bigger segment. So we say point B is between A and C, which means that they're all on the same line. Okay, then we can say that line segment AB plus line segment BC has the same measurement of line segment AC. Notice I did not put lines over those, because without the line, then we call it AB with no line is a measurement. Okay, so if we're talking about the measurements, I can say AB plus BC equals AC, and because there's no line over it, I'm talking about numbers. So I'm saying the measure of AB plus the measure of BC equals the measure of AC. I'm going to put in parentheses here, these are numbers. Let's do some examples. Use the segment addition postulate. Let point Y be between X and Z. So first thing I'm going to do is draw a picture. Here's X, here's Z. Y is somewhere between them. They're all on the same line. They are collinear. If XY is 7, XY is 7, and XZ is 20, X all the way over to Z is 20, find the length of YZ and explain. Okay, well, in order to find the length of YZ, we can use the segment addition postulate, which says, here's YZ, our small plus small equals the bigger one. So I can say XY plus YZ equals XZ. XY was 7 plus YZ equals XZ, which is 20. Oops, I put Z. 20. And then from here, we use the same rules of algebra that we can compute with. So property of equality says I can subtract 7 from both sides. Minus 7, minus 7. So then YZ equals 20 minus 7, which is 13. And this is by segment addition postulate. YZ equals 13. I especially like to go back and make sure that I have answered the question being asked. So I'm going to go back and say, find the length of YZ and explain. I found the length of YZ and I explained how I found it. Let's look at number 2. Suppose A is between J and M. Here's J, here's M. A is somewhere between them. If JA equals 3x plus 2, JA equals 3x plus 2, AM equals 5x plus 1, and JM equals 27. Solve for x and explain. So the first thing I'm going to notice, these two segments add up to the bigger one. So I can say JA plus AM equals JM. JA is 3x plus 2. I'm putting it in parentheses because that is one value. Plus AM is 5x plus 1 equals JM, which is 27. Now I'm going to do collecting like terms. So 3x plus 5x is 8x. 2 plus 1 is 3. And then that same property of equality that I used where we can subtract 3 from both sides. So 8x equals 24. And then divide by 8. X equals 3. How did we find it? We did, again, the segment addition postulate. Okay, let's take a look at our last page here. So why is it so important to be able to tell the difference when we're talking about the segment or talking about its measurement? And the reason is because those are different properties, right? So we said that AB, without a bar over it, is a number. This is a number. AB with a bar over it is a segment. So they describe different things. And so we have different ways of comparing them. We know that we can set numbers equal to each other, but can we set segments equal to each other? No, not exactly, because segments are not numbers. So instead, we have a new symbol, the congruency symbol, that states that these are not numbers, but they are shapes that are match, shapes that match, okay? So this is for when we're saying it's the same shape and size, right? So it's a copy, it's a photocopy essentially, okay? But equal is for numbers. And remember, variables are unknown numbers, and so this could be also for variables, which we're very familiar with. Okay, so if I have two segments, in order to say that their lengths are equal, their lengths are numbers, so I can say that the number that describes AB, or its length, is equal to the number that describes CD. If I wanted to say that the two segments are the same, then I can say segment AB, not equal, but congruent. Segment AB is congruent to segment CD. So an example would be Ed and Ned are twins, and they have the same height. So 5'4" is equal to 5'4". Their heights are the same. But I can't say Ed equals Ned. I can say that Ed is congruent to Ned. Okay, so Ed's height is 5'4". Sorry, that was here. Ed's height is equal to Ned's height, but Ed is congruent to Ned. Okay. Let's take a look at how we can use these congruency statements in order to find out equality statements. So in this example, we want to mark the following segments. We have HI is congruent to JI. So here's HI, here's JI. In order to mark on the diagram to say that they're congruent, we can put a little tick mark. And that means those two line segments are congruent. If line segments are congruent, that means they have the same measurement. So this is saying that HI equals JI. And then we have ML is congruent to LN. ML is congruent to LN. Now, this line segment isn't congruent to JI, so I can't mark it with one little tick mark, but I can mark them with two to say that those two are congruent, but they're not congruent to my other ones. And so we can say that ML equals LN, and so that has a measurement of 7. Then we have JK is congruent to IL, JK and IL. I can't mark it with one tick mark because that was 6. 2 tick marks was 7, so we will go 3 tick marks. Those two line segments are congruent, and so IL must equal 10. So JK equals IL. So what is the measurement of IJ? ij we said equals 6. The measurement of ML is 7. And the measurement of HM, be careful, right? Because IL was 10, but HM is going to be 6 plus 10 plus 7, which gives us 23. So we can say HM was HI plus IL plus LM, which is 6 plus 10 plus 7. Using the segment addition postulate in order to find the total length of those segments. Okay. Another way that we can describe segment lengths is by finding the midpoint, the point in the exact middle, which means that if I cut it in half, the two segments on either side of the midpoint are congruent. So we can say that point M is the midpoint of segment CD. You cannot have the midpoint of a line or a ray because those go on to infinity on either one or both directions. Okay. The other way that we can compare segments is a bisector. Bisector means bi meaning two, sect meaning cut. It has been cut in half. Okay, so this is another way that we get two congruent segments. A line that divides a segment into two congruent segments. So if I say that line R bisects segment JK, it's a J, at point A, then we can say that these two segments are congruent. Now I'm using one tick mark again because this is a different diagram than we were looking at before. Okay, so I can say these two segments are congruent, different diagram, these two segments are congruent. Okay, and then lastly, a couple of examples here. If M is the midpoint of segment AB, where AM, MB, and AB are from this diagram, okay, we want to find the measurements of all three of those segments. So first we have to say, what does it mean if M is the midpoint? If M is the midpoint, it is the point in the middle. In the middle means these two segments are congruent. So we can say AM is equal to MB by midpoint. That's just saying, how do I know that? I know that because M is the midpoint. AM is 7x minus 5. MB is 5x plus 11. From here, we need to solve. So I can minus 5x minus 5x. I also can plus 5 plus 5. 7x minus 5x is 2x. 11 plus 5 is 16. Divide both sides by 2, and so we get that x equals 8. That's not the question that was asked, though, and this is why it's important to go back and make sure you're answering the question. The question doesn't ask for x, it asks for AM, MB, and AB. So we need AM, it's a measurement. AM is 7x minus 5. So now we can substitute in the value of x. 7 times 8 is 56, minus 5 is 51. We also need MB, which is 5x plus 11. Now there's two ways to find this. We can still do substitution. 5 times 8 plus 11, that's 40 plus 11, which is 51. Or you can say, hey, weren't those two segments congruent? So if this one is 51, then this one also has to be 51. Okay, so two different ways we can find that. And then lastly, we also need AB. AB is AM plus MB by the segment addition postulate. So that's 51 plus 51, which is 102. So I've left this little corner, and you don't have to do this, but I like to do this for the notes so that it's easy for you to see. AM equals 51. MB equals 51, and AB equals 102. As long as your answer is clearly denoted, boxed or circled or highlighted, you don't have to write them again. All right, and here's our last example for this notes packet. Given that segment AC bisects segment BD. So AC cuts BD in half at midpoint M, and BM is 4x plus 6, DM is x plus 18, find BD. So we want BD. So since M is the midpoint, I know that these two sides are equal. We can say 4x plus 6 equals x plus 18 because M is midpoint. And midpoint means that the two sides are equal. Minus x minus 6. 3x equals 12. Divide by 3. X equals 4. We're not looking for x, so we need to then substitute this in for BD. Well, BD is the sum. BD equals BM plus MD. So BM was 4x plus 6. MD is x plus 18. Collecting like terms, we get 5x plus 24. X is 4. 5 times 4 is 20, plus 24 equals 44. All right. So make sure that you have a good understanding of this. During the synchronous part of class, I'll be able to answer any questions that you have.